Okay, so my name is Millette, and just a bit about my background. I have a background in pure maths, so I did my PhD in pure maths at the University of Leeds, which is in Northern England. I've worked in venture capital around the place. I also worked for a company called SageCore, which is US based, which sends students to intern abroad at startups, and at Entrepreneur First, if anyone's familiar with them. And I was also a founder in residence on their program. I also separately am a trained opera singer and studied at the Royal Academy of Music for 2 years, but that's not on here because it's slightly less relevant to this.
Yeah, so hi everyone. I'm Sedinam, Sedi for short. I was born and bred in South Africa, so I went and did my undergraduate studies there in economics and statistics. I then worked for a bit as a data scientist at a bank called Investec, and then I moved over to the UK to do my master's in machine learning, specifically within computer vision and robotics at Cambridge, and I was a Google DeepMind scholar there. And then, yeah, shortly after the master's, then Millet and I decided to full-time co-found the Tech Bros. Yeah.
Oh my God, why is it like not? Okay, so welcome to our AI fundamentals class. We are doing this very much from a beginner's perspective, but if you have any questions or anything like that, just shoot them as we go, and hopefully we can answer them. And if not, we'll come back to them at the end. Okay, first of all, what is AI? So Alan Turing first came up with this question in the 50s, basically asking, is it possible for a machine not to answer questions correctly, but to answer them, or necessarily correctly, but to answer them indistinguishably from a human? And this was kind of a big question for a long time, and there's some really interesting theory about the kinds of questions you can ask that a computer will never be able to answer, but that's a whole separate rabbit hole. And so this also links to kind of this idea of, is it possible to create artificial consciousness? And basically, the short answer is not to the consciousness question, but to the kind of an AI mimic a human. The short answer is yes. We have in the past couple of years have these, large language models and ChatGPT that has passed really insane versions of the Turing test.
Mm.
So you can see here you would have kind of an interrogator and they would be speaking to a computer and a human and they wouldn't know who is who. And the question is, can they tell? Uh,
Yeah, and essentially, like what AI is doing today and what it's solving today is basically able to simulate a lot of human behavior. So, in very niche ways. So, if computer vision allows machines and computers to see, and there's things where there's translation software which translates from one language to another. So, this is all basically what AI involves. What big tech are working towards today is sort of AGI, which is artificial general intelligence. And what that means is like a generalization of these AI capabilities across board. So essentially working towards a machine or a computer or a thing that can see and translate and basically function end to end as like a human would, essentially. So yeah, next slide.
oh my God, why is it doing this to me? Okay, so now
Yeah.
what is machine learning?
So machine learning then is a subset of AI. So it's essentially the ability for a computer to execute tasks without sort of human intervention. So essentially, it is teaching a computer or a machine how to do a certain task, and then it being able to do that task and generalize and do that task on unseen data. And then we have deep learning, which is like a more specialized version of that, and just more granular in that sense. Yeah.
So machine learning, I think, it had very specific restrictions, whereas AI can do the data can be any form, and it's sort of stronger in a sense if you have AI than machine learning was more
Mhm,
specific, wasn't it?
mhm.
Yeah. So
Cool. So then essentially within machine learning, which is the topic of today, really, we're going to be looking at learning specifically. There's different subsets or branches of that. So we have something called supervised learning. We also have unsupervised learning, and then we have semi-supervised learning. So just specifically on supervised learning, what that is very analogous to sort of teaching a child, about the world around them. So if I have shapes, so if I have a square, a circle, or a hexagon in this case, and a triangle, and I say to a child that this is a square, this is a triangle, this is a hexagon, eventually the child will learn to generalize without me saying that this is a square, that this is actually a square. And in the same way, that's how these machine learning models learn. So you have your data, and then you have your labels associated with that data. And then essentially here in the middle here, we have this model training. And then the key is that to test it out or to test that if the machine learning model's working, you have this subset of data called your test data. Your test data cannot be used in the training process of the machine learning model because then it would have already seen that data and then essentially, instead of generalizing, it might just learn patterns in the data. So what you want is a separate train set, and then you want your test set to test that what it's learned is accurate. So in this example, we have the shapes, we have the associated labels, and then we have this test data set, and then you see that it outputs, okay, a square is a square and a triangle is a triangle. So then we have essentially within supervised learning, basically what I've described is a classification task, and that's with discrete data. So we wanted to predict the label there, and that's how it sort of happened. We also have regression tasks, which is with continuous data. So not everything is discrete, as I'm sure you all know. And a good example of this would be like if you're wanting to predict the price of an Airbnb, that's a continuous value. And then you have sort of variables, dependent variables, things that, the price would depend on. And in our example, we've said location, time of year, number of bedrooms could be predictors for the price of an Airbnb, but that could be whatever arbitrary variables that you want to define. And the key thing here is, like I mentioned before, you have the sort of train and test sets. And then also the distinguishing thing between classification and regression is the way that you measure the accuracy. So with a classification task, you would measure it on accuracy in terms of like the label that it provides versus the label that it actually is in reality. With a regression task, you use something called the mean squared error. And that's obviously a numerical term, and that's if I've predicted that the price of an Airbnb is $200, but it actually in reality is $100. That $100 difference is the error, and essentially what you want to do is minimize that mean squared error, so it's as close as possible to the true value. Then we have unsupervised learning, and this is when you don't provide labels. So essentially, you just have your data, and the key thing here is that the machine learning model needs to learn to recognize patterns within the data. So I'm not telling the machine learning model that these sort of circles within with on the left-hand side are different from each other. I'm just giving it the data. It's learning through different methods. And then here, specifically what it's doing here is clustering into these three categories. I'm not saying that this is, these are blue circles, these are purple circles, these are red circles. It's just learning to recognize that pattern. And I think then to link it back to the example we had before with the shapes, in this case, it's unlabeled. So I'm not telling the model that a square is a square and a triangle is a triangle. I'm just providing it with images, and then it's learning to group the images into these are all squares, these are all triangles. So that is what unsupervised learning is.
Cool. So now on to
Kami
recommendations.
sending naman.
Sorry? Okay, on to recommendation systems. Basically, anytime you interact with anything on the internet, you are probably exposed to a recommendation system. So, anytime you're on Netflix or on YouTube or anything like that, there's a lot of search results, and it needs to decide, like the website needs to decide what order is it going to show it to you. The OG of this is called Google's PageRank algorithm, actually named after Larry Page, rather than the fact that it's web pages, but it's like a fun fact that it kind of the name applies to both. And basically, the way the PageRank algorithm works is if you imagine, so this is just like a graph representation of websites. So imagine each of these blue circles is a website, and each of these pink lines or these arrows is a website hyperlinking to another website. So if this website here has, I don't know, 1, 2, 3, 4, 7 hyperlinks to it, and this one only has 3, then the one with 7 is going to rank higher. So basically, it ranks pages based on how many other pages link back to that page. That must mean it's a more important page. So that's kind of it's a very simple recommendation system, and I think now it's been upgraded, and there's obviously all this paid sponsored content that goes at the top whenever you search and all that stuff, but this was how they did it originally, and it was like this for a very long time, and I think there's still elements of this now. So basically it gets a little bit more complicated when you're working with something like Netflix, where it's going to recommend stuff based on all these different factors. It's not just like how many people have referenced this film, right? So there's a couple different ways that this can be done. Um, the one on the left here, content based, is basically just to do with your own behavior. So if you're watching Netflix and you've watched I don't know, a film that has it classifies as like this is a rom-com, this I don't know, it's got certain actors in it, whatever the kind of criteria are, and you've liked it or you've watched it multiple times maybe, then it's gonna decide what to recommend to you based on your previous behavior. Whereas collaborative filtering is a different kind of method where basically you have two different people, and let's say we watch a lot of the same films, and then Sedi watches something without me having watched it, but she watches something else and likes it, then it might recommend it to me because it's assessed that we're really similar people. Okay, so yeah, do you want to talk about the content based?
Yeah, sure.
Yeah.
So essentially, like Millet said, it's basing the recommendations are based off of things that I've watched previously. And this could be essentially the features you use to describe this could be really different. So it could be that I've watched, Bridget Jones, for example, for an hour, and Bridget Jones is similar to The Notebook, and therefore it recommends me The Notebook. But the method that we're going to look at today is something called term frequency, inverse document frequency, and this is using text description. So I can have a written description of what Bridget Jones is. I can have a written description of what the Notebook is, and essentially what this TF-IDF sort of matrix tells us is that how relevant is each word in the description of that specific film. So in the Notebook, how relevant is the word like diary or love, and how relevant is it in the Bridget Jones film as well? And essentially, it basically will compile this into a matrix, and essentially also just a sort of side note is that we work with matrices a lot when we do anything within AI or computer vision or AI machine learning, because it's easier for sort of computationally for computation time. It's a lot faster to do that. So instead of working with like separate vectors, we always just compile things into matrices, and we apply operations onto the matrices just to make it more computationally efficient.
And just as a reminder for anyone who hasn't done this kind of maths in a very long time, a matrix is literally just like a spreadsheet of numbers. So instead of having like a list of numbers in some more complicated way, it just arranges them in like an array like this. And that's it.
Yeah. So then once we have these, the TF-IDF sort of arrays or organizing this matrix, what we do is we calculate something called the cosine similarity, which Millet will touch on in more detail later. But essentially, the higher that cosine similarity is between the two films, the more likely it is that that film will be recommended to me. So yeah, that's what this is.
Cool. So now we get to do some fun maths, which I hope everyone is super excited about. So we're going to start with TF-IDF, term frequency, inverse document frequency. So this is going to tell us, basically, we kind of want to do this for every single word. And this is going to tell us how important that word is, and how much of a keyword it is in that particular film description. So we're going to start with TF, term frequency. So this is super simple. All that means is how often a word appears in a document. So you can calculate it by this formula. And as you can see here, we have TF, and then this is the word W and the document D. So basically, you need the word and you need the document. Those are the two bits of information you need. And then you look at the number of times the word appears in the document, and then you divide that by the total number of words in the document. Super simple. So let's take an example. Here is, I don't know if you guys can read this. It's very small. Can you guys read this? It's not that important if you can read it. But we have an example here with a little piece of text. It says, I am artificial intelligence. I'm running for president of the United States. And then it talks about why it should be president. So this document here, it's a very short document. Let's say our word is running. It appears twice in this document. And there are 69 words in total. So the term frequency is 2 over 69, which is around 0.029 point something. So that's basically it. That's how you calculate term frequency. So it's just how many times does that word appear over the total number of words. But okay, so then we have this thing called inverse document frequency, which measures how important that word is, right? Because not all words are going to be weighted equally. Um, so basically, if there's a word that appears in lots of different documents, then that word is going to be less relevant, even if it appears a lot of times in this particular document. So as an example, let's say our word is the word the. So that appears, oh, I thought I had it highlighted. It appears 4 times. In a minute, it's going to appear highlighted where on here. Um, but okay, so the appears 4 times in this document. So our term frequency is 0.058. But the thing is, so that would imply that the is a more relevant word than running, but running is more specific, whereas the appears in everything. So how do we counteract that? By this inverse document frequency. So term frequency will tell us how common is that word to the document. Inverse document frequency will tell us how rare is that word in general. So yeah, the is such a common word across the board that having the term frequency for the have it be this doesn't really tell us much. So how do we calculate inverse document frequency? So the way we do this is we have this function log, which is the logarithmic function. I'll put it up on here in a second to remind people what that looks like. But basically, you don't necessarily need to know. You can just in any kind of calculator or Wolfram, you can Google it, log of something, and it'll give you an output value for that. And basically, what you're looking at is the total number of documents at the top, and in the bottom, you want the total number of documents containing that word. So let's say that we had 20 documents, and this document here was one of those 20 documents. And let's say that the appears in all 20 documents, as it probably would, but running only appears in 3 of them. So then IDF of the is log of, and then at the top we have the total number of documents 20. At the bottom we have the number of documents containing W, which is 20. So we get log of 1, which is 0. But IDF of running is log of 20 documents at the top, and then over 3 documents contain the word W. So that's log of 6.67, which is around 0.82. So this basically, again, gives us kind of a range of values for, is it a common word? Is it a rare word? How much weight should we assign to each of these words? So just as a reminder, this is what the log function looks like. So it's kind of like it's the exponential function, but it's the inverse of that. So it's over here. And just a note as well that because we've got the total number of documents at the top and the number of documents containing this word, this thing here is always going to be greater than 1. So this thing here is always going to be positive. So you're never going to have like a fraction that's less than 1, basically. So this thing here, the IDF is always going to be positive. So hang on. So that we can ignore this bottom half of this graph, basically. So anyway, so that gives us these 2 values. We have the value telling us how often the word appears and then how important it is. And then in order to come up with this TF-IDF kind of joint term, we multiply those 2 things together. That's it. So TF-IDF of W comma D is the term frequency times the inverse document frequency of W. And bear in mind that this is for a specific word and a specific document. So that's why it's a function of these 2 things. So you'll have TF-IDF for a specific word in document 1, and then that word in document 2, and you can have all the different words, and that's why you end up with this big matrix. So in our example here, with the and this document D over here, this is, you just need to remember the pieces of information that we took together. So here, the TF for that was 0.058, but the inverse document frequency was 0. So the total TF-IDF is 0. Whereas for running, the term frequency was 0.029, and then the inverse document frequency was 0.82. So that gives us the TF-IDF of that is 0.024. In a minute, we'll get more intuition on what these numbers mean and why they're relevant. But basically, you'll get this number for each word in each document. You can calculate this thing, and then you can see basically how important, how relevant is that word? What are the most important words that describe this film, let's say? So yeah, basically, if it's a higher score, then that word is more important. If it's a lower score, it's completely irrelevant to that film. And that would make sense that the word the is irrelevant to pretty much every description out there. So now, this is kind of the two bits of maths that we need is this thing called TF-IDF, and then we also need something called cosine similarity, which is basically a way of calculating how how similar two of these documents then are. So let's say we have these 10 film descriptions. So we've got two here and eight more here. And we want to calculate how similar this one here is. D1, a clumsy British woman awkwardly navigates her career, family pressure, and embarrassing love life while keeping a brutally honest diary of wine-soaked regrets. Sorry, not diary two. Document two is an old man reads emotional diary entries about young love, heartbreak, emotional growth, and two wildly different people who fall in and out of love. So let's say this is our set of 10 kind of total documents, and we want to see how similar D1 and D2 are. So let's pick some words. If we were a machine, we could probably do this with every single word, but we're going to pick a couple for like illustrative purposes. So we're going to start with the word and, just because, again, this illustrates that and is very meaningless because it appears in all of these documents. We're also going to look at the word love. So love appears in some of these other film descriptions, but it also appears in these ones, and it appears here twice. And then finally, diary, which only appears in these two. So just to kind of recap, we have 10 total documents, and appears in all 10 of them, love appears in 4 of them, and diary appears in 2 of them. So this was in the previous example, we kind of made these assumptions. Now we're going to like look at a really concrete example. So just as a reminder, the term frequency was the number of times the word appears in the document over the total number of words in that document. The inverse document frequency is the total number of documents over the documents containing that specific word. And then the TF-IDF is just those two things multiplied together. So let's just do it for each particular document. So the first one here, document 1 has 24 words. Document 2 has 25 words. And we're going to start with the word and. So term frequency for and with document 1 is 1/24, which gives us this number here, 0.042 approximately. And in document 2, we do the same thing for and, 1/25, that gives us a slightly neater 0.04. We do the same thing for love. So the term frequency of love here, exactly the same thing as for and, because it also appears once, so 0.042. And for document 2, love appears twice, so 2/25, so 0.08. And finally, for diary, the term frequency here is also 1/24 because they each appear once, 0.042. And over here on this side, diary appears once as well, 1/25, 0.04. So these are the term frequencies for these 3 words across document 1, Bridget Jones, and document 2, the notebook. Okay, so that was the term frequency. We'll now do the IDFs for them. So this is something that we do just for a word rather than for a word and a document. As a reminder, we do log of, so there's 10 total documents, and then we divide over the number of documents that that word appears in. So here we have log 10/10, which is 0 again. Then for love, love appears in 4 of them, so log of 10/4, which is 0.916. And then diary, log of 10/2, so that appears in even fewer of them, 1.609. So basically you can see that as the word appears in fewer and fewer documents, the inverse document frequency goes up and up and up. So it really corresponds with, this word is very rare, so it's very important to this film, versus this love, sorry, listen, this word is love and it appears in like half the films out there. Okay, so now we do the TF-IDFs, and remember you do it for the word and the document. So for and, it's 0 for both. For love, for the first document, it's this number times this number, so 0.038. For love in the second document, it's this number times this number, 0.073. Diary in the first document, it's this number times this number, so 0.067. And then diary for this second film, it's this number times this number. So then you can kind of see what the most important words are to which description, and you can see the most important one here is love that appears twice in this one, but in general diary is weighted quite highly, but actually love appearing twice is weighted even higher. So, okay, so now let's carry through those values for the TF-IDF. So these six values down here, 0, 0, 0.038, 0.073, 0.067, 0.064, all of these like last calculations we did, we'll carry those across so, and basically group those together. So we have all of the calculations for this first film description, we'll put those together. So we've got for the first film description, we've got 0 for and, 0.038 for love, 0.067 for diary, and vice similarly here for the second description. Okay, so now we're gonna turn this set of three values, we're gonna basically group those values together into a vector. So what that means is we can just like list them all together in a list like this. So the first one is going to be referring to and, the second one's going to be referring to love, the third one's going to be referring to diary. And that just means we have like one piece of information essentially to deal with instead of three. And we're going to do that for, we're going to call this one A up here, and we're going to call this vector B down here. And now we can calculate how similar these two descriptions are. Super fun. So this is something called cosine similarity. And it's calculated like this. I'll explain what all this means. So cosine similarity, basically, okay, so if you have a vector like this, these three, so I said it makes the information simpler, and it means that you only have one piece of information rather than three different pieces of information. And that is true. The other thing is this gives us a point in space. So if you've worked a lot with vectors before, you will be familiar with something like this. So when you have a vector that has kind of three different coordinates, it's kind of like when you're plotting in a graph, but it's 3D, and this number of dimensions can go up really, really high. And basically what we're trying to do here to figure out, if you imagine you have this kind of 3D space and you're plotting all these different, there's like a point in 3D space for each film. And you want to figure out, are the 2 points close together? What's a way of doing that? Well, if you look at the angle between those two the 2 points. So if you imagine here's the center, you've got this 3D space. This is really hard to do like with my hands, but you've got this point here and you've got these different points in space and you're drawing vectors. So you've got lines going from the center to all these points. If you've got 2 points, if the angle between these two lines is really small, you can conclude they're close together. But if the angle's really big, they're really far apart. That's basically what we're doing. So, and cosine this is a function that basically will give us a nice neat value. So what we're going to end up with here is that if the angle is really big, we're going to have a number closer to 1. If the angle's really small, we're going to have a number closer to 0. So we're going to have a really nice kind of neat result. And this is defined in this way so that we can have a nice neat result. Someone just decided this is a good way to define it, right? So let's calculate the cosine similarity between this document here and this document here. So the first thing we need up here is something called the dot product. The dot product is a way of multiplying together two vectors, and you basically just multiply each entry by each entry, and then you add the results together. So super simple. So we've got 0 times 0 plus 0.038 times 0.073 plus 0.067 times 0.064. So this is what it's going to look like. And then we're going to end up with this result over here. And that's called the dot product. It's just there's different ways of multiplying together vectors, basically, because it's like a lot of information and you can multiply it together in different ways and get different pieces of information back. So that's what we've got on the top half here. Then below, we've got basically the size or the length of these vectors. So that's what this symbol here means. So if anyone remembers Pythagoras' theorem from a long time ago, and you've got that if you've got a right angle triangle like this, you've got that this thing squared is equal this thing squared times this thing squared. So therefore, this length is the square root of this squared plus this squared. It's basically a generalization of that. So you can generalize that into n dimensions. And so this value, modulus of a, is the square root of all of these things squared added together. And we just calculate that and we get this number here, 0.077. And we do the same thing for b. So basically, those are the pieces of information you need to calculate cosine similarity. So we need this dot product that we calculate here. We need the length of the vector A, and we need the length of the vector B. And then we multiply. So basically, let's get this onto a kind of a fresh slide. But these are the 3 bits of information that we've taken from here. And then we'll take that across to the new slide. So yeah, again, this is what we've just calculated for these 3 things. And then we do like the cosine similarity here is this one over this one times this one, which is 0.945. And as we said, it ranges from 0 to 1, with 1 being really, really similar and 0 being really different. So this is a really long-winded way for us to have discovered that The Notebook and Bridget Jones are kind of similar films. Um, I think this might be a good point to just check if there are any questions on this. I don't know how easy it is to see. There's some people in the chat. Let's just see if anyone's. Does IDF have any relations with inverse matrices? Um, of what? So inverse, maybe. I mean, inverse matrices are just some neat things you can use when you're doing matrix calculations. They're kind of a tool, so I think it might depend on the context of that. How much maths do I need to know to learn and apply AI/machine learning? And people have said a lot. I mean, okay, full disclosure, I have a PhD in maths, so I really like maths. So like I like talking about maths, but you can probably also approach this without understanding all of this. But I always think it's better to understand it,
It's
right?
good to understand the fundamentals. And
Yeah.
I think that once you understand basically what's happening under the hood of all of these algorithms, then you have essentially like you have so much strength and like power in like figuring out like once you're writing up an algorithm where it's going wrong, like you're able to decode a lot of things. But you'll see in the sort of notebook portion of this that we go through this in a very simple way, in the same way that we've done the maths step by step. But then ultimately, there are packages that exist already that people have coded up. So you can actually just implement a package. But again, it's really key to understand what's under the hood, because if there's ever an issue you're having with the package, or if there's something that isn't quite adding up, it's good to be able to go to the source code and understand really what the authors of that package have done. So this is, might seem daunting, it might seem complicated, but it actually is quite simple if you break it down like step by step. And I'd like definitely advise, going through this again. And you'll see in the notebook as well that we'll break it down quite simply. So yeah.
Yeah, and someone also said, what is the cosine similarity for again? So that's to work out basically okay, so there's like these two, just to recap, there's these two pieces of information. The TF-IDF is basically something that you have for each word and each description, let's say, or each document, and that tells you how relevant that word is for each document. And you can end up with kind of this whole, so actually that's the next slide here. So you'll end up with this kind of whole matrix, big set of information where for each word you can see how relevant it is to each description. So you can see love is relevant to a few of them here. It shows up in Harry Potter, Titanic, The Notebook, and Bridget Jones from our set of films, but it's different. It's relevant to different amounts for each one based on the total number of words and how many times love showed up. Diary is irrelevant to the majority and isn't relevant to any of them because and is such a common word. So basically, we end up with this big, big, big matrix. That is the TF-IDF matrix. Then what you do is you can look at an entire row like this and another entire row like this, and then you can calculate the cosine similarity. And what that will tell you is how similar those two film descriptions then are.
And then the more similar they are, the more highly likely it is for that to be recommended to
Yeah.
you. So yeah, the key thing is that the TF-IDF matrix is done like across all words in the whole description. So we've just chosen three here. We've just said, let's look at the word and, let's look at the word love, let's look at the word diary. But actually for every single text description that you have, every single word has this TD-IDF thing. And then you do the cosine similarity between the films. So you're doing it between Bridget Jones and The Notebook, for example. So yeah, it's just if you can visualize it, I think maybe the slide sort of brings it together in that sense.
Also,
So
here we only have 10 films,
mm,
and you would have, hundreds, thousands of films, thousands of words. So you have this huge, huge amount of information. So it's like, how do you then decide what to recommend? And and something else to note as well is just to touch on that, obviously, then the way that we've chosen to describe these films is then going to be really relevant to what's then going to be recommended. So, for example, all of our descriptions earlier. I don't even want to go back because I feel like it's about 20 slides back. But in all of our descriptions earlier, they were kind of light-hearted, short descriptions, slightly jokey. So that's going to give different results than if you describe it like I don't know how they're typically described. And that means that you definitely will introduce bias in the way that you've chosen to describe these films, or the pieces of text that you've used. And we've already we've seen through things like ChatGPT that there's so much bias that it's really hard to see kind of with the naked eye, but in pieces of information and text and things online, you do get kind of these biases that skew. So you could end up with, you can see how that could end up biasing the sorts of things that you're seeing in a maybe more serious setting than just like looking up films on Netflix.
Yeah. I think this is a good point to sort of move over to the notebook.
Should we double check there aren't any more
Yeah.
questions? Um, thank you,
Ah,
Anna.
amazing. Yeah.
Um, oh,
Ah, okay.
you
This is
guys.
just all love. We love it so much.
We love you. Um,
Um,
okay.
okay.
So cosine similarity calculates nearest ba neighbor based on TF-IDF. Oh no, so it doesn't calculate the nearest neighbor. So you that is work that we need to do, unfortunately. So basically, you pick two. So you could pick like The Dark Knight and Titanic, and then you could calculate cosine similarity. Um,
But
but like
yeah, essentially
if you
it's
do all the pairs,
yeah.
you should be able to
And
like
then
order it.
sort of rank it. Yeah, exactly like that.
Yeah.
You order it in what's most similar to least similar, and then you can also just decide arbitrarily how many recommendations you want. So if you want top five recommendations, it'll take, the top five most similar to this film. So it's just it depends on what you want. Yeah.
Okay, and then this last
Um,
question, IDF has any connection to inverse matrices? So yeah, again, inverse matrices are just a very generic thing. It's just like a tool that we use. So if you have a matrix, you can then get the inverse of that matrix so that when you multiply those two matrices together, you get like an identity matrix. So it's just a tool. So I'm
mhm,
not sure that IDF has any specific connection to that.
mhm. Um,
What about words that are similar? Oh, that's interesting. It's a
That's
good
a good
question.
question.
Yeah.
I think so. Basically, you can do TF-IDF on a word level. Basically, you can choose how to define your tokens, right? So if you want to do it on word by word, then it would be different words. So tech and technology and technological would be different words. But if you want to do it on a token level and you want to break down the tokens into four pieces, for example, and the token is tech, then tech would be picked up across the three. So it actually, that's a really good point. It depends on how you define your token. Um,
Thanks, guys, for all the love.
and all the
This is so
questions, these are
kind.
great.
Yeah, good
Yeah.
question. Do you
Um,
use eigenvectors and eigenvalues with this concept? So eigenvectors, eigenvalues, these are all like really, really useful things that you'll probably use in linear algebra at some point. But I don't think you use it in this concept. So basically, just to go, I can just explain that really quickly in case anyone cares or is interested in eigenvectors, eigenvalues. It's oh my God, I shouldn't have done it like this.
there's too many
So
slides.
it's like, I'm just trying to get the one up. Where's the one that has the cosine?
The graph.
Yeah, the 3D
I
graph.
think you've
I
gone.
think I went past.
Oh,
Here it
no,
is.
here we go.
Okay, so basically, an eigenvector is literally just wherever this point is in space. If you imagine like you've got a vector here, and this is the 0.00, um, if you imagine that the vector, you create a vector that's unit length, that's pointing in exactly the same direction. That's the eigenvector pointing in that direction. So that's all that is.
Mhm,
And so you can have an eigenvector pointing that way, pointing that way, pointing that way. I'm not sure it's like that. It's something that's used that much, but
mhm,
I'm not. Yeah, I don't know. It's a good thing to know about, but like I don't know if
mhm.
you wouldn't necessarily use it here.
So
A
Anna asks
token
about a token. So a token is the way you choose to represent like either the word or the thing that you're looking for, essentially. So
in code.
in code, sorry. So a token could be the word itself, it could be one character, it could be four characters. It depends how you want to break down what you want to search across, basically. Yeah.
Cool. I think there aren't any
Okay.
more questions, so I think yeah, this might be a good time
Okay, so
to
should
go
I
to the notebook.
switch to
Yeah, so if I stop
let me
sharing,
share from my side? Um, okay.
oh, hang on, do we both have the video on?
We don't, but I think I can talk through it.
Oh no, we don't. We don't.
Yeah,
Sorry.
so you
Okay.
can see us
Sorry, we've
on
got
this
our laptops
laptop and
next to each other.
then
Okay.
okay, so here, oh, I'll share, let me quickly share the link to
Yeah.
this
If you send it
notebook.
to is it this?
Yes, yeah.
Okay, so everyone can open this notebook up.
Please let me know if you can access it. Yeah, you should be able to. So we kind of start off with just importing necessary packages. So package Oftentimes, it's just a piece of code that someone else has written that sort of generalizes or simplifies, common pieces of code that are used often, and then we can just access them by importing them instead of us writing every single thing that we need from scratch. So these are some like just common packages that we normally use. Specifically, NumPy and pandas are really good because pandas isn't here, but that's for data frames. With NumPy is just to do all your like little maths calculations. Um, so what
Math
we
is probably also
and
good for
math
math
is
math
good for math. Yeah.
calculations. Yeah.
So essentially what we have here, so what we're going to be doing in this notebook is essentially implementing the TF-IDF example that Millet just spoke through. So we're using the same 10 descriptions that she spoke through, and then we just doing it in code. So essentially we have the documents, which are all the descriptions. So there's 10 descriptions here. The first two are the ones relating to Bridget Jones and the notebook. So just so that you have that in your mind. Next, what we do is we split the description into words, or like I said here, tokens, and we also remove the punctuation in all the sentences. That's because, the punctuation, if you have the word,
We actually had a problem with it as we were
yeah.
doing it. So yeah, we can explain to you guys. So it was coming up with love wasn't showing in the second one for some reason.
Mhm.
And we were like, why is love not showing up as one of the words?
And it's because it included love and the comma. So if you remove the punctuation, it's all these like little things sometimes with coding that's it's just important to like make sure you go back and actually understand and iterate, etc., etc. But basically we remove all the punctuation, and that's what this bit here is doing. And then we made everything lowercase again, just to make it as simple as possible for it to pick out the similar words. And essentially, we're splitting all the sentences into like different words or different tokens. So when you print it out, this is what this is doing. So you can see the first document up here, and you can see that in this first sort of array, it split up everything, and you can see it's all lowercase and all the punctuation is removed. So you see like a clumsy British woman, like it's all separate.
Oh, do we need
Um,
to tell people if you want to run this? So basically, um,
it's a collab notebook.
yeah, you need to press. Do we need to say this to people now, or that you need to like?
Yeah, you can just run it on the side here, or you can
Oh, there's a
shift
little play
enter.
button.
Yeah.
Yeah, shift enter. That was
Yeah.
it. Someone has
Um,
said maybe because of what is rejects?
I'm not sure what
Is that one of the
so the
packages?
package, yes, so for the syntax relating to this package, um, yes, that's probably why the punctuation's included. I think that's what you asking. Yeah, yeah.
Mm.
But
Ah,
yes, yeah, yeah. But again, there's different ways to do it and different packages you can use. So this is just the way that we've chosen to implement it. Then essentially, next what we want to do. So now we working towards the term frequency, right? So what we want to do is count the number of times that the word, and in this example, we've used the word diary specifically. We're trying to make it as simple as possible. How many times the word diary appears within the first, well, within the descriptions. So we've just got a simple for loop. We iterating through each of the words in this array of words, and we counting how many times diary appears. And in each text description, you see that diary appears once in the first description, diary appears once in the second description, and then diary doesn't appear again in the rest of the descriptions. And that's similarly what we saw in the example that Balette showed on the actual slideshow. Um, then to calculate the actual term frequency, what we want to do is take the count over the length or the number of words in the array is what I'm trying to say. And essentially then what we get, so all I've done is basically added this line here, this TF value line into the for loop, just, breaking it down so you understand. And we get 0.041666 and then 0.04 for the second, and then zeros the rest of the way. Then to calculate inverse document frequency, we can just use document frequency and then do the log. So essentially we say like if the word diary is in all the words, then we basically add we sum it up, and then if not, it adds a zero basically. And then we do exactly what that math calculation was that Millet showed with log of the number of documents, which is 10 descriptions, movie descriptions, over the document frequency, which in this case will give you 1.609.
Which is what we got on the other document.
Yes.
I've just been thinking as
Yeah.
well, I'm going to download,
Mhm.
I'll send you guys like PNGs of some of these formulas that we've just had as well.
Yeah, yeah. So you can sort of
Yeah,
relate it to what we're showing here.
yeah.
And then we move on to calculating the actual TF-IDF, which again is just the multiplication of that term frequency value and the inverse document frequency. So all I've done is added in a line that shows you this is what the TF-IDF is. And when we print it, we see for the word diary, remember this is just specifically for the word diary, we see that it's 0.067 in the first description and 0.064 in the second description, and then it obviously doesn't appear again in all the other descriptions, so it's zero for everything. And then here, and perhaps this is we'll leave you to sort of play around with this, but this is it's all grouped together, and it's for the three words that we went through in the actual slideshow. So it's for the words and, love, and diary. And what you see is that this is what it outputs, which is exactly what again we showed. So I don't know if at this point what I'll do is I'll also speak through the cosine similarity, and then we'll probably leave, a couple minutes for you to play around with the notebook. So essentially then what we want, we have these vectors or arrays, and essentially what we want then is to, oh, I've just added a new
Oh no.
a new cell, which you don't need. Essentially what we want to do is group, like Millet said, into the three, we want to group the three terms into the one. I feel like I'm explaining this badly.
No, no, no.
Like,
Yeah, no, you are. You
yeah.
no, you're not explaining it bad. Sorry, I think
Yes,
you're
I am.
explaining it well. What I was
Yeah.
saying, you're explaining it well.
Yeah.
So basically, this is all the ands, this is all the loves, this is all
Hmm.
the diaries, but we want to group them the other way. So we want and love and diary for the first one. Then
Hmm.
we want and love and diary for the second
Hmm.
film, and love and diary for the third film. That was what you were
Exactly.
saying.
Yes, that's
You was
exactly.
exactly the same words.
So this is just a snippet of code just to do exactly that, and just to rejig it so that you have the three words grouped in threes, basically, is what I'm trying to say. And that's what you see down here. So you have um this first term here, the second term here, and the third term here grouped into the first array here. And basically now that's the array, or that row in the matrix that relates to Bridget Jones. And then similarly, this is the one that relates to the notebook, and so on, so on. And then we simply just calculating the cosine similarity between every single film. But in this example, what we've done is we've just said, okay, between description one and description two, or document one and document two, which we know we've said is Bridget Jones and the notebook, what is the cosine similarity? So we're pulling out those specific vectors in that matrix. I've just printed them down here, so you see that it actually does relate to the first two um, entries in the big list, and then simply doing np dot, which is the dot product function from the numpy library. We're doing the norms, which is also in the numpy library, and that's the bottom of that equation, that cosine equation. So essentially what we want is the dot product over the norms of the two vectors, and then we print that, and then this is the cosine similarity of 0.945, which is exactly what was shown on the slideshow. The key thing here, though, is that we've shown you this sort of step by step and really broken it down, but actually a lot of this can just be implemented with built-in packages. Even the cosine similarity is in a library called sklearn. So sklearn is the library that has majority of the machine learning functionality. So you don't actually need to even go through all of this, but again, it's really good to understand what's under the hood and actually how you would manually compute these things, just so that you actually have a core understanding of what you're doing when you're implementing anything in machine learning. So yeah, I think now we will switch back, or actually, I think we'll give you 5 minutes to just play around with this notebook,
Maybe 10.
or maybe even
What
10.
what what you
Yeah.
should do is try, because you can see.
Let me scroll up.
Yeah, and you can ask us questions throughout, but
Hmm.
basically what you want to be trying to do in this time is because I mean, yeah, you don't need to understand each line of the code, but we've tried to really break it down. But
Hmm.
if you go, for example, we're on this section here that you're on
Yeah.
with diary, you can replace that with any word. So we've picked love, diary, and I think it was, or
Hmm.
the and, but you can pick any word, and you can see if you can add more words when it gets to the array section further down where we had
Hmm.
like a list of three. Maybe you could have like 5 or 10, and I think a
To
fun
see how it
challenge in the next
changes.
10 minutes is see if you can find two descriptions that are more similar than the ones we don't know what if there's an answer if there are
Yeah.
some that, but see if you can find a pair that are more similar than the ones that we've yeah, where you can get a higher cosine similarity.
Yeah.
So we're going to leave that for 10 minutes. In the meantime, I'm just realizing I don't have it as PNGs, so I'm just saving these pages as PNGs and I'm going
Hmm.
to paste them into the chat so that you can go back to like the content in case anyone like didn't screenshot in the
Yeah.
moment. But yeah, we'll send that through
So
now.
yeah, I'm gonna stop sharing for now, and then we'll check back in 10 minutes.
Hang on, let me which page are we on? Let me send this through so people can actually get started. Wait, sorry, once again, Zoom is. Tell me if this works. Oh, this is looking good. Okay, here you go. So this is just how my brain works, so it's all over the place. But this is the slides that we've just covered, so that if you want to like revert back and compare how things line up, and yeah, do shoot us questions. But yeah, feel free to kind of mess around with it and see if you want to change little bits and just see what happens. I think that's the best way to try
Hmm.
figuring out with code.
Oh, thank you.
Oh, that's our direct message. Someone sent a really nice direct message. That's why we were saying thank you for everyone who got confused. So okay, let's um add the rest of these. Oh no, that I accidentally sent that as a direct message. Sorry.
Let's change it here.
Yeah, to everyone.
Um,
I'm sorry, this is like we're demonstrating our capabilities with Zoom are not quite the same as
Meeting group
yeah,
chat. Yeah,
thank
there
you.
we go.
Your computer.
Computer to.
How do I run this program? Do you want to talk through that while I
So it should be if you have a Google account, it's basically on Google Colab, and you'll be able to go through it, and essentially all you have to do, it should automatically activate like a runtime, which is just like CPU within your computer within Google Colab that allows you to run things on it. And then you just execute it by pressing the play button on the left-hand side, or when you're in a cell, you press Shift Enter and it will execute every line.
But you need to do them in order because when
Hmm.
Seti sent this to me earlier and I was like doing one halfway down and it wasn't working, and that was because I hadn't done them. You have to
Yeah.
start at the top, execute each of them, so like press play on each of them all the way down,
Hmm.
and then um, that should then work all the way through.
Hmm.
But yeah, let us know if there are any issues with that. And I'm just going to
Yep.
add the last couple pages. Are we on 5? I think we are.
Hmm.
Yeah. Okay, so we're going to give you until quarter 2 to and if, also send messages if you find any that are anywhere near close to what was it we got 0.945. But yeah, if you can find one that's higher, then you get a cookie, a virtual cookie.
Yes. An
Cool.
emoji
An
cookie.
emoji cookie. We're gonna mute for 6 minutes.
Cool. Cool.
Okay, awesome. It is quarter two, so we're going to restart. Out of curiosity, have people been using other words, right? So we had like love and diary, but did you try with different words as well? People still here?
Yeah.
I kept getting errors.
Oh,
Um, let us know what the errors are and we can
yeah.
try and help. Yeah.
We'll come back to it.
Well,
Yeah.
yeah,
Yeah.
we'll give another kind of 5 minutes. Was just reading the
Cool.
code. Okay, cool. So I feel like what we can show you love, romance, life. Amazing.
Amazing. Yeah.
Cool. Yeah, because so okay, we can come and revisit things. Oh, the k-means part, that's on us. That's
Yeah, yeah.
we
We still,
forgot to
yeah.
import something, so don't worry.
There's one import, but we're gonna cover k-means sort of
Now,
the theory behind it now, and then yeah, we'll send you the import, which I think is in the chat, but we'll send it again, and then you can just play around with that as
yeah,
well.
we'll give you 2 minutes
Um,
to go back to that.
so yeah, let's reshare and chat through some k-means stuff.
Cool. So this is where we ended up. We looked at
Hmm.
cosine similarity, we looked at these kind of matrices. So now, oh, hang on, I feel like this isn't how I want to do it. Yeah.
Yeah.
Um, so okay, there's this thing. So we've looked at basically what do you, sorry, I'm trying to get this to fit right. We've looked at we have two films and you have these like vectors with a few words that describe each where you look at the relevance of those words to each of these films. And then we can compare two films. As we did here, you can compare like this one and oh, I've just realized this is in the wrong bit. The D1 and D2 should be up here. That is on me. I will tweak that, and before sending the PDF out, I will just also this PDF is going to be huge, so there's that might be a problem, but make sure you have a lot of free space if you want to download it. Anyway, okay, so for the k-means algorithm, basically this is a way of taking, instead of just looking at two things and seeing how similar are they, let's say we have a bunch of films. We might want to look at kind of how do we group them together into clusters? So this was something we were talking earlier about as well with unsupervised learning. You might want to cluster things together without kind of necessarily knowing why, right?
Mm.
I don't know if this is exactly
Yeah,
the same,
yeah.
but
So like you wouldn't know that, let's say you don't know that Bridget Jones and The Notebook is a rom-com. Is there a way for us to cluster them in the same sort
group
of group
regardless.
regardless? Yeah.
Yeah.
So this
So
is an algorithm to do that.
yeah,
Yeah, yeah.
exactly. Yeah. So here, for example, this is a really, really simplified version of how you might think about it. So here we've got 2 dimensions. And as we said before, with these vectors, they're n-dimensional. So they go up into really, really high dimensions. But in our example before, we had this kind of 3-dimensional, and love and diary. Here, imagine it's 2-dimensional. So we've got love and we've got armor. And we're assuming that every film that has armor in the film has armor in this text description for some reason. So you might have like Iron Man here, you might have Lord of the Rings, anything where they wear armor. Let's say that that's just described in the description. So you might then end up with a bunch of kind of fantasy, MCU kind of films up here, and then over here you might end up with rom-coms or romance films, and then you'll have films that are neither. So let's say these are the only two things that we're looking at. You might end up with clusters like this. Realistically, this is way, way, way
So
oversimplified.
oversimplified.
Yeah.
Yeah, yeah.
But like you might still have these kind of clusters. And so the k-means algorithm is a way to basically decide how we're going to then cluster these things,
Hmm.
which Seti's going to talk about.
Yeah. So essentially how we start this off is that we choose essentially the number of clusters that we want. And we can do this arbitrarily. We can do this based off of prior knowledge. So if we kind of know like, oh, in the whole scope of, the movie world, there's only 3 genres that exist, then we can say like we want to group these things into 3 genres. But again, there's also mathematical ways to determine how like what the optimal number of clusters are. So definitely search something called the elbow method. There's a whole lot of things that you can like use to optimize the number. But for now, let's just assume that we choosing um 3 genres. And essentially what we then do is we randomly initialize these sort of 3 points or these 3 clusters, or what we call them as centroids, so like the center of a cluster.
So that's the center
Um,
of one of the clusters.
yeah,
And this is the
exactly.
center.
And then what we do is that we calculate the distance between each centroid and then each point or each film that exists within the space. Again, this is so oversimplified and it's only 2 dimensions, and it actually is way more complicated than this with like all the different dimensions. But we calculate the distance between, the word or the centroid and then every other point in the space. And then what we do is that oh, we assign those points to the nearest centroid. And then essentially what you want to do is recalculate what that centroid would be. And what we do is then we average all the newly assigned points and then calculate a new centroid. So then once we've done this, we see that there's like all the purple. So this is the centroid, one of the centroids, and then we have these points being the closest to this centroid, and then same with this, and then same with this. Once we recalculate the average will shift, and then essentially now you have that this is the average of these new points. And essentially what you'll do is you'll iterate and basically redo this process until your centroids stop changing. So until you get to a point where um, everything you can see here it's color coded. So like everything that's purple, is up there and the centroid and the clusters haven't changed. So this is kind of
Oh,
like
this X would be slightly
it
higher,
would be
probably, but
slightly
yeah.
higher, yeah, but it's just for illustrative
Yeah.
purposes. And then we've basically condensed the algorithm here into a couple steps, exactly what I explained. So selecting your number of clusters, selecting the centroid, assigning all the points, and you do this by calculating the distance, assigning it to the nearest cluster, and then calculating the average, and then repeating this until the cluster stop changing. So that really is the k-means algorithm, and that's a form of unsupervised learning. So it's a way that you could take these TF-IDF vectors, and then, or this matrix basically, and then use k-means to cluster the films together. Um, and that's, under the assumption that you don't know what the genre is or what it's clustering on. So
I think now we're back
are
to,
we
oh,
back to
we've got
code?
build your own. Okay, this isn't great. You don't have to build your own algorithm, but we're going to go back to the notebook, and we're going to send you a new link. Sorry, not the notebook, the film, the Jupyter notebook on Python
Yeah.
that we shared earlier. So Sadie's just going to
Just give
share
me a
a
second.
new link that has
So
this last bit corrected.
all this has is like the import of the k-means replace screen share.
Oh yeah,
All this has is the import of the k-means, which I've imported up here. So it's from sklearn.cluster import k-means. And like I said, a lot of the packages are within a lot of the machine learning related packages are within this library called sklearn. And then all we do is literally run it. Like
yeah.
there's really nothing more complex than this. We've initialized the number of clusters to say there's only 3 genres that exist in the world, and that's an oversimplistic version. We've actually named the documents now. So we've said, okay, the first description relates to Bridget Jones, the second description relates to the notebook. And then we've said, implement the k-means algorithm, use 3 clusters, which we've decided assigned up here. And then the random state, what that is essentially whenever you run this algorithm, there's some sort of randomization involved. And therefore the initialization of the centroids, for example, can change every time you run it. But what it does when you set a random state, you can choose any arbitrary number, but it's just so that you have reproducible results, so that if I run it on my side and then you run it on your side, you have the same result. And that's just a way of like using random numbers in computers, but it's not really that random. And once you run the k-means algorithm, you fit it to the different documents, and then that's all you do really, and then you output this for loop just outputs what document was assigned to what cluster. So you can see that Bridget Jones and the notebook were assigned to the same cluster 2, but then interestingly you see The Dark Knight, Iron Man, Toy Story, Ratatouille, and Frozen all assigned,
And Back to the Future.
and Back to the Future all assigned to cluster 1. So obviously there's not only
And Harry
three.
Potter and Titanic, those two famously
So
similar
dissimilar.
films.
Obviously there's not only three genres that exist. We have defined the fact that there's three genres that exist.
And we've only based it on
Um,
these three words. So what's interesting now,
mm,
yeah, sorry, someone asks, is k-means used in supervised or unsupervised? So yeah, we were saying it's a
yeah.
form of unsupervised learning
Hmm.
because you're kind of clustering, but we're not saying these are all rom-coms, or we're
Yeah.
not assigning labels. We're just saying um, which ones are similar. So what would be interesting, if you want to kind of experiment with this, sorry,
Hmm.
I feel like I should do it on here,
Hmm.
is to, if you guys want to try and change, where are the words? Where are the words?
The
Here.
description, yeah.
Yeah, so if you go words of interest and you define the words of interest to something different, you can change these descriptions. You can also change the number of clusters.
Hmm.
You can kind of, um, I feel like you can, that's basically it, isn't it?
Yeah,
Those are the two
those are
pieces of
the
information.
two main things that you can
Yeah.
do. You can play around with that and see, yeah, sort of what clusters together.
What words are the ones that
Yeah,
you really want to be
yeah.
focusing on? Um,
Yeah, and then I'd also sort of encourage going to look at the algorithm behind the scenes of this k-means package, right? Or this essentially in the library, if you search sklearn online, you can see the behind what's under the hood basically. And you'll see it's basically this algorithm, I don't know why I cannot speak. The algorithm that I just explained is what's under the hood, but this is just showing you that okay, we can do things where we do it step by step, but then we also can just implement things that already exist. So yes, that is basically, is that it?
yeah,
Yeah, given a replace,
I'm just gonna, we'll round off now.
yeah,
So, um, hang on.
yeah,
So, I mean, we were gonna give people a couple minutes now, but we may as well
round
round off the
off.
presentation then if you want to keep kind of experimenting with it. And feel free to message us as well on here, if you have any kind of
Hmm.
questions. That's not right.
Hmm.
On the chat.
Hmm.
But yeah, basically to summarize what we've talked about today, we've talked about AI, machine learning, deep learning, how they kind of relate to each other, and what they all are. We've covered supervised versus unsupervised learning, with these nice little visuals. We've talked about content-based versus collaborative filtering. We didn't really go into the details of collaborative filtering because it's a bit more complicated. You have more variables involved, but that's also interesting. Check it out. And then finally, we've looked at, for content-based recommendations, these various things. So TF-IDF, cosine similarity, k-means clustering. So basically comparing two film descriptions and calculating similarities between them, and also
Hmm.
grouping film descriptions based on specific keywords.
Yeah.
And that's basically it. So thanks for joining, to everyone who's here. And yeah, please give us a follow. Let us know if you have any questions, and we hope you enjoyed.
Thank you so much.